Good evening, everyone. I am Shelja Mamgai from Indian Institute of Remote Sensing, Dehradun, and today I'll be teaching you about something about extracting the land features, various land features using the satellite datasets. Uh, we'll be calculating some spectral indices in the Google Earth engine, and we'll be deriving some land cover features such as vegetation, water body, and snow cover. So let's start with the today's lecture. So we'll first start with what is Google Earth Engine. So as you might know by now that Google Earth Engine is a cloud-based platform for doing some analysis, geospatial analysis. It has a lot of data sets, that is a huge volume of data sets available for the entire globe and for a longer period of time based on the different satellites available, publicly available data sets. Then using the Google's computation resources, it can reduce the processing time. So, that is, it can handle a large volume of data sets in a very short time, and it has a massive archive of remote sensing data, the catalog available in the Google cloud. So when we compute any usual index or spectral index, then what we require? We require a satellite dataset. So we first download the satellite dataset using the online available portals. Suppose we want to download the Sentinel dataset. So we'll go to the portal, we'll download the dataset into our system, and then we'll perform the pre-processing steps such as clipping the dataset, the other pre-processing like atmospheric correction, mosaicing of the dataset. But after that, we'll calculate the, let's say, indices we want to calculate, or we want to perform some classification. Then we have to generate our output. But what is the use of Google Earth Engine then? Using Google Earth Engine, you have to write some set of codes. You already have the dataset available in the cloud of Google Earth Engine, and then you can only export, you can perform the analysis and you can export the output as such. So no need to download all the datasets for the your study area. Study area can be small, study area can be large. But using Google Earth Engine, you can perform the analysis for all over the globe in a single click. So this is the interface of Google Earth Engine. This is the code editor. This area is the code editor where we write our codes. This is a JavaScript based coding platform. This is the map of the Google Earth engine. Here, whatever we want to analyze, we want to visualize whatever layers, they will be available. They will be showing in the map area. Then on the left hand side, you can see this is the script manager. That is, all the scripts you write here in the code editor will be saved in the script manager. You can toggle between different scripts you have saved. Then in the API documentation, you have pre-written some codes, some snippets for algorithms, different arrays, etc. And then there is the asset manager, where you manage whatever you have imported to the Google Earth Engine account. Then in the top bar, this is the search area. Here you can search for the different satellites, different data sets, different areas, whatever you want to search from whatever you want from the Google Earth catalog. Then if you want to share your script, Google Earth Engine script, then you can generate a link or a URL from this for the code from here, get link feature. Then you can save your script from here and run your script from here. So these are all the options available here. From the right hand side corner, you can see that there is an inspector tool where you can inspect locations, the pixel values, the objects, whatever have been added to the map. Okay. Then during the code, while writing the code, whatever you want to print, that will be shown in the console. This is basically for the debugging of the code. Whatever you write, if you want to print at each step, you want to see what are the images output, what are the values for the codes, then you can print them into the console. And if you are getting some error, you can easily find out at which step you are getting the error. So this is the use of the console. Then there is the task manager. Whatever you want to export, suppose you have performed the analysis, you want to export your data, final output, then you can give some commands for exporting. You can write some codes here, and the process of the progress of the exporting of the image will be shown in the task manager. Then there are some tools over here on the left hand corner, that is the geometry tools. Here these tools are used for adding the for marking the locations in the on the map, this area, or you can define your study area from these geometry tools. From toggling the zoom in zoom out, you can use this pan, and then there is the layer manager. Whatever layers have been added to the map, you can change the settings, you can manipulate the visualization using the layer manager. You can on off the layers, and you can perform the transparency, swipe, everything from this layer manager. So ultimately, using the Google Earth Engine, you have the satellite images, you have your algorithms, and you can use them together for solving the real world problems. So if we go to the homepage of the like code editor platform, so this is the platform of the Google Earth Engine. This is the code editor, as I said, and here you write your scripts. You can save your scripts from here, you can import your scripts from here only, and then you can perform your analysis. Here is the map where your layers will be shown. When we perform the when we calculate the indices, then we'll come to this part later. Then for the feature extraction from satellite data, we have a electromagnetic spectrum. I'm sure you must be knowing about it. So like in the electromagnetic spectrum, what we have the different range of wavelengths, and the satellite captures in the different areas or different portions of these wavelengths. So we have the gamma rays, X-rays, ultraviolet rays, the visible portion of the electromagnetic spectrum, where which our eyes are only can only see the visible portion of the spectrum. Then there is infrared, the near infrared, shortwave infrared, etc. Then microwave range and the radio waves. So for the feature extraction, why this electromagnetic spectrum is important? So all the features or all the targets, I must say, on the Earth, they have their different response on when they interact with the electromagnetic rays. So these features are extracted based on those responses. So each feature have their unique signature, spectral signatures. So based on those spectral signatures, they make some curves, spectral response curves, from these ranging from these visible to infrared or microwave regions. So using these spectral response curves, we can identify different land cover features. For example, for this today's lecture, we will be identifying the vegetation, water bodies, and snow cover. So this is the spectral reflectance curve or spectral response curve for vegetation, dry bare soil, and water. Now what we can see, it has on the x-axis it has wavelength in micrometers, and on the y-axis it has reflectance in the percentage. So let's first see the spectral response curve for the vegetation. This is that green one, green curve. So you can see that in the blue range, this is which is from the 0.4 to let's say 0.5 micrometers. So in the blue range, it is being absorbed, or it is showing very less reflectance. Then in the green portion, it is having some higher reflectance, let's say about 30%, about 10%, and then in the red portion it is getting absorbed. So since our eyes can only see the red, blue, and green colors, only those colors which are available in the visible portion, so we see the vegetation as green color. But the satellite sensors can capture even more range of the wavelengths. So you can see that the red vegetation is being reflected very highly in the near infrared portion. So it has very high reflectance in the near infrared portion, but low reflectance in the red portion or the red band. So the formula for the identifying the vegetation change or the vegetation, extracting the vegetation from other features, we use these differences, difference for the NIR band and the red band, and divided with the sum of the NIR plus red band, which is to normalize this index. So in this way, the normalized difference vegetation index is calculated by differentiating by differencing the NIR in red band reflectance values and dividing with their sum. Similarly, for the water, in case of water, you can see this is the curve for the clear water, which is being absorbed in the blue as well as in the red band or in the near infrared band, but it has higher reflectance in the green band. So the formula for the NDWI becomes green minus NIR, since it has higher reflectance in the green band and lower reflectance in the NIR band, and divided by their sum. Okay. Similarly, for the bare soil, it has this curve which is showing the higher reflectance in the higher wavelength ranges. Then for the snow, what happens for the snow is, let's zoom in here. For the snow cover, it has higher reflectance in the visible portion, or you can say in the green portion it has the highest reflectance, while when the wavelength increases, it gets absorbed. So in case of snow, it has you can see it has almost 0.8 or 80% reflectance in case of visible in the visible spectra. So the formula for NDSI, that is normalized difference snow index, becomes green minus SWIR divided by green plus SWIR. SWIR is the shortwave infrared band, which is here in this range, that is about 1400 nanometers. Now the satellite data sets we are going to use in this today's practical is the Sentinel-2 data. Okay, I told you about the different bands, that is NIR band, red band, green band, SWIR band. So from where these bands come, how do you identify these bands from the satellite data sets? So all the satellites or different sensors, when capture the data set, they capture the data sets into different bands. So all the information of different bands is available along with the information of the data sets or the satellite data. So Sentinel-2 is a European satellite. It is the data is provided by the European Space Agency, and it is based on the constellation of two identical satellites, that is Sentinel-2A and Sentinel-2B. Individual satellite has a revisit period of 10 days, but since they are twin satellites, this is a constellation of twin satellites, so it provides the revisit time at a particular area of 5 days. So at each 5 days, you will be having an image of your study area. So it has a total of 13 bands. So you can identify from these 3 indices which we discussed right now, NIR, red, green and SWIR band. So band 3 is green, band 4 is red, band 8 is NIR, and band 11 and 12 are SWIR band. So we'll be using these bands for today's practical, and they have different resolutions and different wavelength ranges, which I shown you in the spectral response curves as well as in the electromagnetic spectrum. So now let's start with the coding part. So first step, whenever you start with your any problem you have for the real world application, you want to perform the analysis, you want to perform your coding. So your first step is the study area selection. So how do you mark your study area or identify your study area from the whole global map available in the Google Earth engine? So there are multiple ways where you can tell the Google Earth engine where your study area locates. So first you have to pan on your area of interest. Let's say I'm zooming it in this area, which has which is covering the Dehradun as well as, let's say, from Kedarnath, Badrinath, these much area I want to perform my study in this much area. So one of the ways to import the study area boundary is, we'll go to the assets. We have the option of new. We can import shapefile from here. So if you have the shapefile of your study area, that is a particular defined boundary, then you can select the study area boundary, you have the shapefile, or you can have it in the form of a zip file. You can select it, you can import it. Another way of defining your study area is the geometry tools available here. You can mark your study area, but it will only be marked as a point. If your study area, or you have to mark something, some linear features like road or river, then you can use this feature, which is a draw a line. If your study area has some irregular boundaries, then you can draw a polygon, which is draw a shape. You can digitize or perform it in this area, or whatever you have, any boundary which is having any irregular shape. So for this area, I'll be using the last option, which is a draw a rectangle. I'll click on this and we can draw a rectangle like this. Okay, we can draw a rectangle like this. So here a rectangle has been drawn. This is your study area boundary which we have defined, and variable named geometry has been imported here. With the name geometry, it has the information about the coordinates whatever have been marked. So these are the coordinates in the decimal degrees for this particular boundary which we have just now made. Now you can change the color, you can toggle it as on and off the layer, or you can change the color of this polygon or the rectangle from the settings, edit layer properties. You can go here, the edit layer properties, and you can change the color whatever you want. Let's say we want to have it as red or orange or any color, then the color will be changed. So in this way you have imported your study area boundary. Now the second step is to add the satellite datasets. Now whatever datasets you want to use, it is based on what problem you are solving through your code. So in this practical, we want to extract the land cover features. So we'll be using the optical multispectral datasets, which is Sentinel-2 dataset. So we'll be defining a variable called S2 collection. Then we'll import the image collection, that is ee.image collection, and Copernicus S2. Copernicus S2 is the code algorithm provided by the Google Earth Engine to access the image collection of the Sentinel-2 imageries. Then we'll be defining our study area boundary by using filter bounds geometry. Then geometry is the variable you have defined for the study area. Then we'll be filtering it for the study time period. We don't want to use all the image collections for now. Like Sentinel-2 has image collection based on S2A and 2B. It has from 2016 to till date, or 2017 to till date, based on the satellite whatever you are using. So I don't want to use all the imageries available in the cloud. I want for a specific time period. So I'll be filtering it using .filterDate. Please note that it is a case sensitive language. So if you write .filterDate with small d, then it will show you the error. So it has their predefined coding, it has predefined algorithms, predefined syntax, I must say. So it will work only when you have imported or when you have written the code in a particular case, be it in the uppercase or in the lowercase. Then to define the visualization parameters, how you want to display your imagery, then we define 3 bands. We want to see the band combination. So we'll be defining the band 4, band 3 and band 2. I have defined with again with a variable named S2 bands. So band 4, 3 and 2 is the red, green and blue. So RGB combination it is, so it will be a true color composite. Then since my study area, as you have seen, that study area is a bit large, so it is not compulsory that it will hold only one image, it will cover in the single image. So it can have 2 images, it can have multiple images. So for this we want to mosaic our image, we want to collect our image on this on a particular area, on a study area boundary. So what we are going to do, we are going to define a new variable. Then this is our collection, image collection S2 collection, which we will made already, which we have filtered already for our study area and for the study time period. Then currently it is an image collection. Now we have to use some reducers. Reducers are the like such as mean, median. You can use minimum, maximum to reduce the image collection to the image, so that you can clip the image, you can perform the further analysis to the image. If you want to do it for the multiple images or the multi-band images, multiple images in a image collection, then you have to define another, that is another thing, you have to define a function and perform analysis at each image. So currently we are reducing the image as a median, which is finding the middle value for each pixel, and will be clipping the image to our geometry. So here it was used filter bounds, but here I am using clip. So what is the difference between these two? When we use the filter bounds geometry, then it will collect all those images which are covering or which are falling inside my study area, but it is not clipping the study area. It is not clipping the images to my study area. It is just having all the full extent imagery. But when I use clip function, then only it will clip the study area, images to my study area, and then thereby reducing the size of the images and then reducing the computation time and my resources. So that is why this is the basic difference between the filter bounds and the clip. Now we want to visualize the image, so we have to define the parameters. We have to tell the Google Earth Engine that how I want to see my image. So we'll define another variable called S2 display. We'll define the bands. We have already made a variable called S2 band where we have defined the band numbers, and we'll define the minimum maximum value which we want to get displayed in the image. Now I'll tell you later that from where you can get these minimum maximum values for your image. Now when you have defined all the parameters to visualize your image, or you have prepared your image to for the analysis part, then you have to write the code for adding the layer to the map. So it will be map.add layer. Then you have to define, first thing you have to define is the image which you want to visualize, that is the S2 mosaic, this one on line number 10. Then the visualization parameters, which is S2 display, and some name for your layer, because when it will get added to the map, it will be only layer 1, layer 2 until you define some name to it. So I have defined S2 image. Then it is the last 19th number line code. It is not necessary to write it, but this, what will it be doing is, it is map.center_object geometry. So what it will do, it will just pan your map to the middle of the study area. So in the map, if you don't know where your study area or the polygon lies, then by adding this line, it will automatically zoom into your or pans to your study area. So when we run this code, we'll get the output like this. This is the true color composite, that is red, green and blue band, which we already chose here, that is band 4, band 3 and band 2. So this is the true color images. Now as I already told you about the electromagnetic spectrum and behavior of different objects or different targets based on the spectral response or the electromagnetic spectrum. So based on this, you can see that there is, like, you cannot easily identify the features in this image. So while changing the band combination, when I change it to the false color composite, then you can see that some features are getting highlighted. So if you are little bit familiar with the false color composite image interpretation, then you will be easily able to understand that this is the snow, this is the water, and this is the vegetation. So as I already shown you that the vegetation has very high reflectance in the near infrared band. So that is why we are now visualizing the NIR band in place of red band. Earlier we were doing is the red, green, blue, that is true color composite. Now we are visualizing the near infrared portion of electromagnetic light, electromagnetic spectrum from the red channel. So we are seeing all those things which have very high reflectance in the near infrared band as red now, which is the vegetation. So let's go to this code. From here you can take the screenshot of this code or write this particular link to your browser so that you can also perform the analysis along with me. So when you run that code, it will show you this image. So now this is the same code which I was showing in the presentation. So this is the geometry which is getting loaded. You can see your study area boundary from here, and I have added the using this map.add layer, I have added the layer to the map. So now I can see the layer here. If you want to, this is currently the true color composite, that is the band combination we have mentioned earlier, that is band 4, band 3, band 2. Now if you want to change it to the false color composite, then the band combination will be NIR red and green band. So as I shown you in the in the presentation, that band 8 is NIR, band 4 is red, and band 3 is green. So we have to change it here. We'll just make it band 8. We'll write it in the codes. So band 8, band 4, and band 3. So currently it is showing us the true color image, true color composite. When we run the code, it is now showing us the false color composite, the standard false color composite with the combination of NIR red and green band. Now as I was mentioning about changing or knowing the minimum and maximum values for this image, so in the layer manager you can see you can change the layer properties. When you click on the settings bar, you will have some settings here. You can change the band combination from here as well. It has all the band or the 13 bands. You can visualize other combinations also, like using different bands, like swirl band in place of red band or blue band in place of green band, any combination which you like to see. And for this we have band 8, band 4, and band 3. Now for the visualization point of view, it has some image stretching properties. So they have different methods of stretching the image. So let's say if we want to stretch it for as 100%. So the values for the minimum and maximum will change here, and then you can apply it. So it has, the values have been changed, then you can apply it here, and you can see the image will be modified. It will change a little bit. You can change the gamma properties, you can make other modifications in the image. Okay. So, but this is only for the image visualization. It will not affect the pixel values of the image. And other thing which I was mentioning is this map.center object. So suppose we are in somewhere here, our map is by default is somewhere here. If we comment this line and run the code, then code is getting run. It is showing some image, the code has run, it has shown the output, but you have to pan it, like manually you have to go at that location. But when you add this line map.center object, then geometry, then wherever you are in the map, whenever you run this, click on the run, then it will automatically pans to the image, pans to the location of your study area boundary which you have set, since you have mentioned here as a geometry, map.center object geometry. Okay, so this was the visualization of the image. Now we'll go to the spectral indices calculation part. So first index we'll be calculating is a normalized difference vegetation index. So NDVI, your normalized difference vegetation index, utilizes the difference between the NIR and red band, the reflectance values between the NIR and red band, to highlight or to enhance the healthy vegetation in the images. So as you can see in this figure, you can see that the reflectance of healthy vegetation is shown. So 50% of NIR is being reflected, while only 8% in the red band is being reflected. So difference between the reflectance of these two bands is very large. So the value of the NDVI, that is 0.72, it is coming in the larger area, or the larger value is the coming. Then reflectance of the stressed vegetation. Here you can see it is only reflecting, like it has a reflectance of only 40% in the NIR band and only 30% in the red band. So there is very less difference between NIR and red bands. So the NDVI will automatically come down, since the NDVI is basically the difference of these two bands, the reflectance values of these two bands, NIR and red band. So that is how you know that when the difference is very large between NIR and red band and the difference is positive, then you have the healthy vegetation. If the difference is very less, or the difference is negative, then it is not the healthy vegetation, or it can be some other feature. So this is how you interpret the NDVI. So NDVI is basically an index which shows us the health of the vegetation, and it has the values ranging from -1 to +1. So this was the basic about the NDVI. We come to the coding part. Now in continuation of the previous code, where we have defined our study area, where we have defined our image collection, now we want to compute the NDVI. So we'll define another variable called as NDVI. We take our S2 mosaic, which was our final image prepared just now, and we use the predefined function called .normalized difference. The formula of NDVI is NIR minus red divided by NIR plus red. So Google Earth Engine has predefined function of calculating the normalized difference between two bands. So .normalized difference, in the first band you have to mention the first band, that is the NIR, in the first band of the denominator, that is whatever is having the higher value. So in case of NDVI, NIR bands has the higher values since it has the higher reflectance in case of vegetation. So we'll be mentioning as band 8 or B8 in place of first band, and B4, that is the red band, in place of second band. So the NDVI will be calculated only by this one line code. Another way of calculating the NDVI is this line number 25, 26, 27. Here you can define those bands as a separate variable. Suppose we have defined variable NIR as S2 mosaic dot select band 8 or B8. So here we are extracting the single band and assigning it to a variable. Similarly for red band, we are defining as a B4, and we are extracting the band 4 and defining it as a variable called red, and we are manually writing the formula of NDVI as NIR dot subtract red dot divide NIR dot add red. But this is a little bit longer process, so we usually use this dot normalized difference function of Google Earth Engine, which is already there. So by now we have calculated the NDVI. Now we want to visualize it. So here again I have mentioned some minimum maximum. You can keep it as -1 to +1, and then you can change the minimum maximum values as I showed you earlier using the layer manager. It has a palette, that is a range of colors which I want to see. This will be the, by default this will be the minimum value of the image. Suppose I have mentioned the -0.05. So the values nearby -0.05 will be shown from these colors, and respectively other colors. The maximum value will be representing in this color. You can also write the color names here, but the color names, it takes only few color names. So you can define these variables. I'll also show you how to find these colors or the coding of these colors. Then you can add the layer, NDVI layer, to the map, and you have given the image name, you have given the visualization parameters, you have given the name. Why I have written 0? 0 can be, if you want that your image should not, your layer should not get added by default to the map, then you can add 0 so that you can later on keep it as an on and off. Then here it is calculating only NDVI. It is a basic index. Now you want to extract the features. You want to extract the vegetation from it. So you have to give some threshold. NDVI is having the range of -1 to +1, but you have to define a threshold that above this value is the vegetation or healthy vegetation. So this is the threshold I have given for this image. This threshold is variable, although if you want to highlight or if you want to extract only the dense vegetation or the very healthy and dense vegetation, then you can increase these values and you can give 0.5 threshold or 0.4, 0.6 other values also. So I have given 0.2 currently. Then you can add again, here you added the NDVI layer, now you can add the vegetation layer or only those pixels having the vegetation pixels. So here I have used the update mask. Since I have added, I have prepared a mask of vegetation here. .gte is the greater than and equal to. So NDVI values which are greater than and equal to 0.2 have been added here, and then update mask has been updated, and I have given some color which is the dark green color, and have given the name of the layer. Now till here you have prepared your mask of the vegetation. It has only the pixels of vegetation. Now if you want to export this layer, if you want to export your NDVI or you want to export your vegetation layer, then you can write some few lines codes and just you can export it to your Google Drive and then you can download from here there. So it asks for the image name. You have to define some parameters here. You will define the name of the image, whatever image you want to export. Currently it is exporting the NDVI, which is this layer which you have computed here, having all the values, all the pixels. You can also export only the vegetation layer, only you have to change it as a vegetation. Then description is the name of the file you want to export, like from which name you want to save it in your drive. Here you will mention this. You can give some folder name, and if you don't give any name, then by default it will go to the root of the Google Drive. And if you mention some folder which is not there in your Google Drive, then it will make a new folder automatically with the particular name mentioned. Then region is the geometry, and scale, which is the pixel size you want to export, and then the maximum pixel, which is the limit of the exporting of the image to the Google Drive. So the output of this image will be like this. So it is the false color composite. This is the Dehradun area. So this is the Lachiwala forest area. So you can easily identify it is a forest range, and this is the other feature, or we can say non-forest or non-vegetation region. So after computing the NDVI and masking and thresholding it with the some value, which I had given 0.2 in this case, so here the output will come like this. Only those pixels have been retained which are greater than 0.2, and other pixels have been removed. So here you can see that this river bed has been excluded, river channel has been excluded, all the urban patches have been excluded, other things have been excluded, only the vegetation areas are there. You can also see the vegetation in between the city is also there in the image, since it is a 10-meter band image, so it captures the area quite nicely. So let's go to the coding part. Here the initial part is similar, which I had shown earlier. Only the band combination has been changed, which is the false color composite, and then it is exporting the image, the visualization of the vegetation image. So here you can see in the layer manager, this is the false color composite. We were focusing in the presentation in this area, or we can see, like, suppose we are coming in this part. So this is the original image, that is the satellite image of showing the false color composite. Now we'll visualize the NDVI. This is the NDVI which has not been masked till now. It is showing the complete area. So you can see how the values has been ranging from the minimum maximum supplied to it values, and it is the color palette. How you can identify, how you can display this color palette, you can just change it from the plus sign. If you want to add some color, or you want to change the color from here, let's say currently it is showing the negative most value, it is showing as the white. In NDVI, the -1 values nearing the -1 or the very negative values are the water pixels. So you can see here, this is the water pixels. So this is the white color, it is being shown in the white color. So we want to change the color of this, then you can just keep it as a blue, and you can see here, you can copy this, you can put it in your code part, or you can change it from here also. You can, if you click here OK, then it will change to blue, and if you apply this, then you can see the color of the blue pixels, color of the pixels having the NDVI value very less have been changed to the blue color. So this is the vegetation, which has been masked using given the threshold. You can change this threshold as per your wish, as per your application. Here also you can see that other features have been masked out. They have those pixels apart from vegetation have been excluded from the this layer, which is the vegetation layer. So in this way you can extract the vegetation from the satellite image by computing some index, which is the normalized difference vegetation index. Now we'll move on to the another index, which is normalized difference water index, which utilizes the green and NIR band. So as I shown you earlier that water has higher reflectance in the green channel or green band and lower reflectance in the NIR band. So the formula will become as green minus NIR divided by green plus NIR. So what changes we have to made in the previous code? Already we have written the code for the, we have seen the code for the calculating the NDVI. So formula is similar, only we have to change the band names. So again, here we have to change the band numbers. Earlier we were using the NIR in red band. Here we have to change the bands to green and NIR. Since earlier in the earlier case NIR was having higher reflectance, so it was placed on the first place and red band on the second place. But now formula has been changed, so we have to modify the formula accordingly. We'll be having band 3, that is green band, in the first place, and band 8, that is the NIR band, in the second place. For the normalized difference function, which is a predefined function for the Google Earth Engine. So we have defined a variable called NDWI. We have calculated using the same mosaic, same image which we have made of the Sentinel-2 dot normalized difference, and we have calculated the normalized difference water index. Again, I have written the similar code for another method for calculating the NDWI. Here you can define the NIR band separately, green band separately by selecting band 8 and band 3 again separately, and define the formula manually, which is variable NDWI is equal to green dot subtract NIR dot divide, and then in the bracket we have to write green dot add NIR, which is this formula, green minus NIR divided by green plus NIR. Then again here are the visualization parameters. The minimum maximum we have to set. The colors we have changed. You can, this is only for the visualization, so you can change it according to you. And map.add layer will add the NDWI layer on the map. You have to define the name, what layer you want to show to in the map, and with the visualization parameters and some name to your layer. Now here another thing which has been changed is the threshold. So for NDVI, it has different threshold for extracting the vegetation. For water index, which is the normalized difference water index, you have different threshold for extracting the water. So it can range, all the values greater than 0 are water pixels, but for the specific area, for the specific image, this threshold can be changed, it can be changed very minutely. So for this image I have kept it as 0.06 because it is a very hilly terrain. So all the hill shades or the shadow areas, it also takes it all the shady pixels as the water pixel. So it confuses with them, it gives false information about those pixels. So you can change this threshold based on your image, whatever you are working on. So again we have written the .gte, that is dot greater than equal to 0.06. I've kept only those pixels which are greater than 0.06 or equal to 0.06, and we have made a water mask. So water dot update mask, again M is capital, so it is case sensitive, and water. Then palette I have defined this color is dark blue color, and I have given some name to the layer, which is the water. So what output it will show, this is your reservoir, which is the Tehri Dam reservoir. It is a very large reservoir. You can see the water here in the false color image. So in the false color composite you can only visualize, but if you want to extract this water separately, then you have to perform the NDWI in this layer or the classification also. So after calculating the NDWI, only those pixels and giving the threshold to your NDWI layer, only those pixels which are having water pixels which are greater than 0.02 are being shown in this image. You can see this large reservoir as well as this river channel. Here also this river channel has been extracted. So water pixels have been extracted. So again we'll go to the code. Here you can see it is again the same image we are importing, and all these parameters are same. Now the index has been changed. It is the normalized difference water index. We have calculated the NDWI from here by changing the bands for the formula. As per the formula, we have defined the colors for NDWI, which is currently ranging from -1 to +1, or for this image I have defined the minimum maximum values, and we have given the threshold. So when we visualize this layer, we can go to the layer manager. We can zoom into this area which is having a lesser topography, lesser complex topography. So first we see the false color composite. Here you can identify the water, here some river channels here. So let's zoom into the Rishikesh Haridwar area. So this is the Rishikesh area here, and this is the Haridwar part. So in the false color composite you can identify the water like this. In the NDWI image you can see how the water pixels or water has been clearly shown in this image. This is the NDWI, although currently it has different other pixels as well, which are non-water pixels. So to exclude other pixels we have masked it. So if we mask it like this, let's change the color of the water to, let's say I make it yellow, so that it can be easily shown in this overlaid on this image. So if I make it yellow and change the transparency using the swipe tool here, I just change it like this. So you can see the river channel as well as the canal has been extracted nicely using this water index. Okay. Here also this is the river channel and this is the NDWI water mask. Here you can see that this is also a river channel, but currently it is a dry river channel, since this is, I think, this is the Chandrabhaga river, which is a monsoonal or seasonal river. So currently it is, in this particular image, it is being dried, so it has no water signals or water signatures. So in the NDWI image it is not showing as a water pixel. It is showing very less values, less than 0 values. So after applying the threshold, you can see only those areas have been extracted which has water present in it. Okay, and the river channel, which is dry river channel, it has not come up in this water mask. So in this way you can extract the water, which is a land cover feature, from the satellite images using the NDWI index. Then the final last one is the normalized difference snow index, which is the NDSI. So NDSI works on two bands, which is green and swear band. That is, it utilizes the difference of reflectance of snow in the green, that is, it is in the visible portion, and the shortwave infrared bands. So the formula of NDSI is green minus swear divided by green plus swear. So here what we have to change in the previous formula is the band numbers or band names in the formula of dot normalized difference. So now we are calculating the NDSI, which is the snow cover. So again we are importing the, again we are mentioning the satellite image, original satellite image on which we were working earlier. Then normalized, dot normalized difference, we have mentioned the band names. Band 3 is green band, and band 12 we have kept it here, which is the shortwave infrared band. Then again different methods of calculating the NDSI. You can define the swear band separately and green band separately and give the formula as green dot subtract swear dot divide, then denominator in a separate bracket, which is green dot add swear. So this will compute the NDSI. Both the output from this method and this method will be same. They won't be different. Only the coding is different. It is a single line code. It is a little bit enhanced or expanded code of the 3-line code. Then you have defined the visualization parameters. The minimum maximum you have changed, minus 0.3, 0.8 is the maximum. Then you have added the layer named NDSI. The layer name was NDSI, which we have computed here. NDSI visualization parameters here we have defined. Then we have given the name NDSI to the layer, and then we have defined again a variable called snow. Since right now it was till now it was the index NDSI, but now if we want to extract the feature of snow from our image, then we have to give it again some threshold. So this threshold you can change according to you as by visualizing it from the image, and I have kept it as 0.35 for this image. Now we'll update mask and we'll extract remove all those pixels, all pixels which are not snow. We have given it some color and given it some name. So the output of this particular NDSI will be, so this is the false color composite, same image zoomed into the different region which is showing the snow cover areas or the glacial areas. So this is the output of the mask of the NDSI. So these are the snow cover areas which have been extracted, which have been shown in some different color. Now you can, let's zoom it here. You can see there are some white pixels you can see here. These have not come in the as a snow pixels because these are not the snow, this is the cloud cover. So NDSI is very well able to differentiate between the snow and cloud pixels, and which the normal human eye or by visualization it is difficult to differentiate between the cloud and snowy pixels. So by calculating the NDSI you can easily differentiate that what is the snow cover, what is the snow index, what is the snow cover or the snow pixels in this area, and what are the cloud pixels in this area. So these will get distinguished using the NDSI. So again let's go to the coding part. Here the similar same code which I was showing in the presentation. Here you can see this is the false color composite of the image, satellite image. This is the Harsil area and the Kedarnath, all those areas which are Gangotri, all the glacier areas or the snow covered areas. So here you can see, although from the image also you can try to identify that, differentiate between the snow and the cloud pixels. You can see there are some differences in between the snow and the cloud, but you cannot extract it easily by this image only. So you calculate the NDSI, which is the snow index. So you can see that these areas are having different shades or different colors. Why they have different colors? So because they are having different values which are very much differenced or very much different from these areas which are non-snow pixels. Then we see the snow cover. So these are the snow cover areas. Okay. So in this way you can also again toggle the swipe the layer, toggle the transparency of the layer to see the snow covered areas. So in this way we have calculated the NDWI, NDVI and NDSI to extract the features of snow, water and vegetation. In this layer we can also see the difference. Is there any difference between these two methods? So let's just comment this line, which is variable NDWI, and we have calculated the NDWI from using this formula earlier. So now let's calculate it using these three lines, NIR, green and NDWI. So NIR band I have defined as band 8, green I have defined as band 3. Formula I have given as green dot subtract NIR divided by green dot add NIR. Similarly, in the NDVI case it was here as band 4, 8, 4 and 8 and 4, then the formula of NIR. So we'll uncomment this and comment this line. When we run this code and see the NDVI, so it is again showing the same layer. However, we have changed the NDVI, we have commented this line and we have calculated the NDVI from this enhanced or extended version of the code. So this is the same, both the methods are same, only difference is the algorithm or the syntax part. So you can write a 3-line code, or you can use the predefined function of dot normalized difference to compute the NDVI. So in this way, we have calculated we have extracted the land cover features using the spectral indices based on their unique spectral signatures, unique spectral response curves. So this was the snow, and thank you. This was all